Okay, so sorry for the technical problem. So before we have the lunch, let's talk about super optimizations. So this is a work, I'm from UC Irvine, so this is a work I done when I was an intern in MediaTek in Boston. And here are my colleagues, Stan and Vitz. So this is the outline today. So first of all, we're going to introduce Super, the framework we're going to use today. And the second and the third part, we're going to talk about two different problems when we try to use Super in our, when we try to use it, and the problem we found, and we propose some solution to solve it. So let's talk about Super, the Super optimization we are going to talk today. So Super is an LLVM-based super optimization framework done by a group of amazing people. So some of you might know what is super optimization. So assume you don't know. As a well-paid, well-trained engineer, the best way to find the thing we don't know is to ask Google Translate. So Google Translate tells us that super optimization is a fancy methodology to discover and synthesize people rules autonomously. So we know people, right? People is a transformation that replaces one code fragment with the other. But how do we do this autonomously? Like how do we do this? So to answer the second question, let's talk about some of the drawbacks of the handwritten people rules or the traditional way we develop peoples. So the first of all is, of course, it requires a lot of manual works to discover potential peoples. So it relies on heuristic, experience, and gut feeling. So the second problem is that we need actual efforts to verify the correctness of the rules, because we need to be ensured that these people preserve the original program semantics. And of course, there's a lot of tools that help us. For example, the Alive, which has a talk this afternoon. And final, of course, is even more difficult to maintain if we have 1,000 rules. 1,000 rules all comes together, it will be a problem. So the super optimization is basically trying to solve this problem automatically. So the first key characteristic is that it will systematic search for potential peoples from the input code. So you give it an input code, and it will try to generate peoples. And second of all, it will try to verify the generated peoples by formal proofs. So of course, these are just two of the most important properties that super optimization have. And of course, there's a tons of implementations. And the framework we're talking about today is one of the implementation. So it's a super optimization framework based on LVM. So it performs super optimization on LVM bitcodes and generates peoples. So currently, it supports a subset of LVM instructions. So for example, the memory operation load and store is not supported yet. And second of all, it supports several kinds of ways to synthesize the peoples. And here, although we're not going into the detail, but we just highlight that we are focusing on the instruction synthesis, which use an algorithm called CGUS. And finally, it tries to prove the correctness of the people it generated by SMT solver. Okay, so here's the workflow of Super. So on the top, you'll see that we will give it input code, and you will try to do the synthesis. And after it do the synthesis, it will come up with a bunch of peoples, and it will try to ask that whether these people will bring a performance benefit. So that's the cost evaluation part. So if it doesn't have benefit, it just started over again. And after this part, we will try to verify to see whether it preserves the program semantic. And of course, if it doesn't pass this verification, it will just start over again. So this is a workflow. And last part of the introduction, we're going to talk about some terminology we'll keep using in this slides. So by saying LHS, we mean a small code fragment extracted from the input code that when we perform super optimization to synthesize, or sometimes we'll call it inference, we will get RHS, which is another code fragment. We try to use it to replace LHS. And of course, this pair of LHS and RHS, we call it a peoples. So that is the terminology. So that is the introduction of Super. So now we're going to our first problem when we try to use Super. So the scenario we're going to talk here is that we're going to use Super like offline. So we like use Super offline, and given the exactly same program, LVM program, we fit it into our compiler and we fit it into Super. So after that, Super will try to come up with a bunch of peoples, right? So these peoples are specifically tailored to the input code. And finally, like we hope to like after we generate a bunch of people, we try to integrate it into InstCombine in LVM. So that is the scenario we're going to talk about here. So to give a motivating example to show the problem we're going to talk about here, we're going to look at this example in LVM IR. So here we have LHS and RHS, and the green tags are the tags Super will try to replace. So here, Super tries to replace a percent result on the LHS, which is a select instruction, with two other instructions on the RHS, the %3 and %result. So like seeing this picture, you might wondering why Super think that replacing one instruction with two instructions is a good thing. It's like in terms of performance. So to explain this, let's briefly talk about how the cost evaluation works in Super. So in this red dotted box, it uses a cost function here. So this cost function, the input, the inst star I, is a code fragment, either the LHS or RHS. So given a code fragment, it will try to get the cost of the operation, the get op cost function. So this get op cost function is basically a simple fixed table lookup. So for some expensive instructions like select multiplication, floating point, or division, it will return either 3 or 5 for these operations. But for the rest of the instruction, it will just return 1. And after getting the cost for the operation, it will recursively evaluate the cost for the operands. So in most of the cases, this cost function will return the size of the code fragment because most of the cases, instruction costs 1. And after looking at that cost function, we finally know why Super thinks it's a good idea to do this replacement, because it thinks that select is pretty expensive, cost 3. So it tries to replace it with two other cost 1 instructions. So that is this picture. But when we try to look into the x86 assembly, we found regression. So here, apparently, again, the green text is the part that changes. So we found that in the x86 assembly, on the left-hand side, there are only 2 green tags, but on the right-hand side, there's like 4 x86 assembly. So to try to investigate this regression, first, we want to ask ourselves if in the x86, whether the select instruction is still expensive. And it turns out that the implementation of select instruction in LHS in x86 is a C move, which is a condition move. It's actually not so expensive. So the cycle count varies on like a lot of cases, but in this case, it's around like 1 to 2 cycles. Where on the RHS, we try to replace it with a single bitwise OR instruction, which is 1 cycle. So it's not necessarily worth it to like replace around 1 to 2 cycle with a single cycle instructions. But even that, we have a question that why we generate more x86 assembly instruction on the RHS. Like we have 2 on the LHS, but have 4 on the RHS. And to answer that, let's put part of the RHS, LV, and IR side by side. So here, when we look at the RHS, the green text and the purple text, the bitwise OR instruction, and the purple text is a floating point comparing instruction. Both of them use one like single x86 instruction to implement it. But when we look at the %3, which is a sign extension on the condition of like the condition register from the floating point comparison, it used 3 x86 instructions to implement it. Where on the LHS, it only takes 2 x86 instructions to implement select. So now we know why you have regression on the x86 assembly, because apparently like Super don't have enough knowledge on the target is lowering to. So of course, this is our problem. Like these LV and IR-based people do not always like improve performance in the target machine code. So And so most of the time, it requires the human filter to filter out those people that didn't bring a performance on your machine code. So because from the example, we see that there's some regression on the machine code, so we want to like apply an extra instrument on the machine code after this pipeline to see whether people really benefit on our target. So here we use a static program stats. So in this static program stats, we want some like key numbers. The first one is the approximate cycle count. And about like this approximate cycle count, we want to as close as the real result. So we hope that it can include some microarchitecture effects, especially first, the multi-issue in modern processor, and the pipeline hazard. So we want to include this effect in our approximate cycle count. So therefore, we use LVN MCA for this static program stats. So LVN MCA is a tool now available in the LVN project. And it will basically statically measure the performance of the machine code for a specific CPU. So it will take the assembly as an input and output the approximate instruction cycles. Of course, it can output a lot of like other extra information. For example, the hardware resource pressure and the dynamic instruction scheduling states. But the approximate instruction cycles also take these two effects into account. So that is what we're hoping for. And also here we define the benefit. So the benefit we keep talking in the rest of the slides is basically the approximate cycle count here of the original program and subtracted with the cycle count after apply a certain peoples. Okay, so let's do some experiment to see what happened, like how many people has a performance benefit on the x86. So here is our baseline experiment background. So here we use the single source folder or the single source benchmark in the LVN test suite. And we split like one function per file, so there's a total of 1788 functions. And rest are our configuration. So we put some timeouts, and we use part of the components during the synthesis. So here's the result. So we have a total of 1788 function or files. And we found about 257 peoples. But surprisingly, we found that not every peoples like bring a benefit. So around 43% of land bring like non-positive benefit, which amount of the, like in this 43%, around 25% bring the negative benefits. So, well, that is not what we want because now we need like a human filter to filter out those either the 43% or the 25%. So we're wondering like why this happens and how do we solve it. So the first most intuitive way we have is like whether there's a problem or can we fix the cost function. And so if we want to fix a cost function, here is some more like extra background here. So we talk about the cost evaluation parts. Now we want to talk about the how do they decide benefit and how do they interact with the synthesis part. So here, the has benefit function is basically the ground diamond box. It's pretty simple. It basically compares the LHS and RHS cost. And on the synthesis loop, the loop here in the like red dotted box, when we finish one synthesize, it will return a bunch of, we call it RHS candidates, which is kind of people candidates. And we will try to enumerate these candidates to test it whether it has a benefit compared to the LHS. So that is how the loop working. Okay, so now we know more details about how the cost function works, right? So, and we also saw that the cost function didn't have enough knowledge about our target architecture. So that we have a really simple idea. What if in the cost function, we try to use the entire backend to evaluate the machine code performance? What if we put the backend into a cost function? So here is our approach. So pretty simple. First of all, for each RHS candidate, which is a people candidate, we clone a module for it. And we try to apply a single candidate people to the clone module. when we generate the machine code of this clone module, and we evaluate the LVN MCA cycle count as the cost for this RHS candidate. So that is our approach. So here's the result. So first, the most notable thing is that we found that there is 0 negative peoples, which is what we expected, because we basically use the same measurement, the same LVN and MCA measurement into our cost function. So it makes sense that we don't have any negative regression peoples anymore. But notably, on the positive peoples, we found that there's nearly 4 times more peoples found. And also, in the total amount of people, there's also a huge amount of increasement. And the most important of all, these 570 peoples are all positive peoples. So no human filter requires now. So also, some people will think that, well, whether running a backend in the cost function will take a lot of time. And it turns out that, no, it basically takes the same amount of time, although the timeout rate is a little bit higher. So it brings, let's go to the second and the last question we have. Here, to show this problem, let's go back to one of the examples in the baseline regression. So here we have a more simpler peoples, which replace 2 instructions with 1 instruction. So it kind of makes sense, we replace 2 by 1. But again, and also this code is embedded in the for loop where the %IV is an induction variable. But again, when we're looking at the x86 assembly, we found regression. And there's 2 parts of difference in this code, the red part and the purple part. So here also we show the LV and IR here. So the first kind of difference on the red part is caused by the instruction selection difference. So when we look at the RHS, it used 3 x86 instructions to implement the 3 LV and IR instruction. However, when we look at the LHS, the %1, %2, and %result will reduce to single x86 instructions. So that is the difference here. That explains why there's only a single x86 instruction on the LHS. And where on the purple difference is basically caused by a strength reduction. Because actually the %0 subtraction will be vanished because of the strength reduction. Yeah. And we're not going to talk more about the purple parts because it's about the classic compiler phase ordering problem. So we're more focusing on the red difference, where to look into detail, we know that we can reduce %1, %2, and %result into a single BT instruction. However, Super doesn't know that. So Super tried to replace the red box with, well, another RHS, which would destroy the blue box and generating a suboptimal machine code. So that is a problem. So if Super can look at a larger context, looking at all the 4 instructions, it can figure out it's probably not a good idea to do the replacement on the red box. So from the previous example, we know that a people need to apply on a context. And by saying context here, it's basically the predicate when we try to integrate it into InstCombine. And also, actually, the previous backend cost function, we're using the whole module as the context. But of course, we're not going to use the whole module because it doesn't work well when we try to integrate it into InstCombine. So the question here is that how do we find a proper context? How do we reduce the context from the whole module? So we basically propose 2 ideas here. One is reduction, which from the whole module, we try to reduce to a minimum region that brings possibility benefit for a people. The second one is the opposite direction. We try to expand it from the LHS to find a proper context. So the first idea, we try to leverage bug points. So if you don't know, bug point is basically a tool for compiler developers to find some crashes in your LVM passes by reducing the input IR into smaller region. So how we use this bug point in our context is that in the normal usage, the bug point will or your compiler will crashes if there's some bug in your LVM passes. So the bug point will find, will try to reduce a minimum region that caused the same crash. So how we use it is that we made an artificial crashes when we found an interesting people, so that eventually bug point will like reduce a minimum region that will bring a positive benefits. So that is the reduction part. However, when we simply try this method, but some problem we have here is that the bug point didn't reduce like enough context, like didn't shrink enough context to a region we want. And the second idea is going from the opposite direction. So here we try to expand it by starting with LHS, and we try to add a source and sink instruction, which is an instruction that prevents this code by eliminated by that code. So starting from here, we try a different like sink instruction or source instruction to see how different instructions affect the benefit of this LHS. And if it doesn't work well, we try to expand the region. So the brown inst here is from the original code. So we still preserve the source and sink instruction, but we add more instruction from the original code to see whether a certain region is a proper context. And of course, we will follow the depth use chain, the SSS depth use chain to expand our region. So that is our idea on expansion. So there is, of course, some open question. First of all, we observe some noise when we use the MCA to measure the performance. Most of them are due to register allocation or spilling. And we found that the context issue we mentioned in the last part, it doesn't appear in all of the cases. In some cases, people is either benefit or like negative. So because if there's a context issue, people will be benefit in some of the, will have positive benefit in some of the cases and have negative in other cases. And as you've seen, we haven't run the benchmark after applying the people, and we're wondering what is the outcome of like actually running it. And of course, we're wondering if we can measure a code side instead of performance. And finally, as we introduced in the background, we only use subset of the RHS components. So we found the Super is actually pretty sensitive of what component you use. So how do we select it? How do we select a proper set of RHS components? So input welcome. Yeah, these are open questions. So here's a summary. So basically, Super needs a more precise probability test with regards to the performance of the machine code after apply a certain peoples. And we found that there's three primarily like characteristic affect this machine code performance: the target ISA, the people context, and the optimizations. And we found that by simply integrating the backend into your cost function, it can bring about 4 times of improvement of the amount of positive benefit people you found. And also, we present 2 ideas of like how do we find a proper context autonomously. So, yep, I think that's it. And the MediaTek Boston office is hiring for both full-time and interns. So thank you, everyone.
Time for 1 or 2 questions.
So what about moving Super into the back end? And where you were actually working on machine code, and you don't have to worry about the context issues. The optimizations are done, and now you're looking for just code changes. And so now the feedback loop can be much tighter.
So you're saying we can possibly move it into working on the MIR, the machine IR?
Yeah, make it an MIR pass. That's traditionally where people optimizations have been done.
Yeah, correct. Yeah, that would be an interesting idea, but I think the concern is that Super is originally designed as like a target independent Super optimizer. So I'm not pretty sure whether like affect the portability of super like across different architectures.
So that's a challenge, right?
Yeah,
The challenge is to design some, it might not be super, it might be M super. But,
yeah, M super.
Right.
Yeah.
But the challenge would be to make it table driven.
Yeah, that would be interesting. Yeah.
Sorry, I'm going to do something with bad matters and respond to the previous questions really quick. Super's pretty good at creating dead code, so you really do want to run something like that in the middle end. You also want something like it at the back end, right? We want more of these tools. But so I just wanted to say this is really cool, and this is some stuff that we have always wanted to do in Super and haven't gotten around to. That cost model you showed is the kind of crap that I made up at one point, and we know it's bad. But the question I had is that I just wanted to ask, what if you just do this for all of InstCombine and InstSimplify? I mean, why, there's plenty of bad stuff in there too. What happens if you call LLVM MCA for all of the rewrites that LLVM wants to do?
Oh, we never tried it. You're saying like applying LLVM and MCA on the InstCombine rules?
Yeah, I mean, there's plenty of unprofitable stuff there too. It's not just Super that makes bad decisions.
So yeah, we definitely haven't tried that.
Okay, I'd be super curious if you do.
Yeah, I'm thinking like maybe we can add some like toggle on each of the InstCombine rules to see. Yeah, that'd be cool. Yeah.
Any other questions? Okay, great. Let's thank Min, and I think it's
Thank
time for lunch.